Okay, so hey guys, how's it going? So today I'm going to be going through my video on photon interactions, and I have 14 questions to go through with you guys today. So it's a longer video topic. So I'll probably be splitting up into two videos. In the first video, I'll cover questions 1 through 7. The second video, I'll go through 8 through 14. I'd say each video will probably be around 25 minutes long or so. I've made the questions in such a way that I think it's a great review, um, over the topic of photon interactions. But also, I think it's excellent to go through these problems. If you're studying for a large exam, take the board exam, the ABR Part 1, 2, or even 3. So with that being said, let's begin. Okay, so problem 1. Write down the formulas for each mode of radioactive decay. So A, beta plus decay. So essentially, you have an element in which a proton is changing to a neutron. So the atomic number is decreasing. You have an electron to balance out the equation. And also the creation of essentially it's a positron. And you have a neutrino with beta plus decay. So in beta minus decay, what's happening is a neutron is changing into a proton. So the atomic number will gain 1. You have your beta minus decay, which is comparable to an electron. And also you have an antineutrino. So in electron capture, essentially what's happening is an orbital electron is interacting with a proton and creating a neutron. So the atomic number is decreasing by 1. In pair production, you have a photon interacting with an energy greater than 1.022 MeV. This is the threshold. It's creating a positron and an electron. There's no change in the mass number or the atomic number. For E, internal conversion, what's happening is an element in an excited state is using some of that energy and removing an electron. In F, gamma decay, what you have is an element in an excited state. The nucleus is excited. It's releasing that energy in the form of a gamma ray. In G, which is alpha decay, what's happening is the element is decreasing an atomic number by 2, decreasing a mass number by 4. So essentially it's decreasing 2 protons and 2 neutrons and creating this alpha particle. So for H and I, these are very common questions. What does electron capture compete with? It competes with beta plus decay. So notice here in electron capture, proton is converting into a neutron. Look at beta plus decay, proton converting into a neutron. I, very common question. What does internal conversion compete with? It competes with gamma decay. Look at internal conversion and gamma decay. Both start off with an element in a higher energy state, and they release that energy through different forms. Okay, so problem 2, part A. So what are the 4 main types of photon interactions? So we have photoelectric effect, Compton effect, Rayleigh scattering, and pair production. What symbol designates each of their linear attenuation coefficients? So for photoelectric effect, we have tau, Rayleigh scattering sigma r, Compton effect sigma c, and pair production or kappa. For C and we'll do C and D at the same time. And that is what are each of their energy dependencies and what are each of their atomic number dependencies. So for photoelectric effect, the photoelectric effect portion of the mass attenuation coefficient is proportional to the atomic number cubed over the energy cubed. For Rayleigh scattering, proportional to the atomic number over energy squared. Compton effect, proportional to Z over A, and then 1 over HV for at high energies. Pair production, proportional to Z, atomic number. For HV, there's a threshold at 2 MO C squared, 1.022 MeV. It increases a lot past this threshold, but then eventually it starts to level off at high energies. So for E, now we're going to go through some different examples, and you're going to tell me what's the most dominant interaction at each of these examples. So I, for Z60, energy 1 MeV, most dominant interaction is Compton. For 2, Z80, HV 10 MeV, most dominant interaction is pair production. For 3, Z10, HV 10 keV, the most dominant interaction is photoelectric effect. And the last one is a little bit trickier. It's so Z10, HV 10 MeV. The most dominant interaction is Compton again. So by looking at, say for example, 4 in this particular case, it can be a little bit tricky to gauge sometimes. So I would recommend that you almost memorize the plot of the different dominant regions. A common question too that sometimes tricks people is they might ask, like, remember that these are just dominant regions, right? So in the Compton effect dominant region, there's still some photoelectric effect happening, but the majority are Compton effect. It's Compton effect dominant. So sometimes that concept can trip students up. Okay, so for problem 3, we're going to be calculating the linear attenuation coefficient, mass attenuation coefficient, atomic cross-section, and electron cross-section. And I've given the values for each of the interaction coefficients, given the atomic number, the atomic weight, and the density of lead. And this will be for 2 MeV photons in lead. So let's go ahead and calculate the linear attenuation coefficient. Essentially, all you're doing is adding up all the different coefficients. And for mass attenuation coefficient, you're just taking that linear attenuation coefficient and dividing it by the density. Now for atomic cross-section, it's a little bit trickier. This is going to be a formula you want to memorize, but you may be more familiar with it just in a different rearranging. I know it with mu over rho on this side, and the atomic cross-section as the numerator over here. So let's input the values, and we have our solution. Now for electron cross-section, all we're doing is taking the atomic cross-section and dividing it by the atomic number, or number of electrons. We get our answer. Okay, so for problem 4, given a plot of energy versus mass attenuation coefficient for carbon, and focusing in on the Z-dependencies, calculate the photoelectric, the Compton, and the pair production regions of the mass attenuation coefficient for lead at each of these energies. So we're going from carbon, which is this plot. So part A, this will be at 0.1 MeV. So let's go to 0.1 MeV for carbon right here. What's our mass attenuation coefficient? It's about it's 10 to the negative 4. So we got that. But what's the Z dependency at 0.1 MeV for photoelectric effect? It's Z cubed, right? So we can go ahead and write down each of the elements atomic numbers, and we go ahead and cube it. We get our answer of 3,000. So now we can set up a ratio from that carbon value with 3,000, and we'll see what we get. We multiply them. We get 0.3 for lead at that energy. Approximately. But what's the real answer? It's 0.4 lead. So very close, essentially, just by going by that Z dependence. For B, we're looking at 1 MeV. Let's go ahead and go to 1 MeV, right about there. And the coefficient, mass attenuation coefficient for Compton. So we get about 6 times 10 to the negative 3. Dependency is Z over A. So we can calculate that. And we'll go ahead and set up a ratio. Multiply it by the value. And we get our answer approximately 4.7 times 10 to the negative 3. That's our answer calculated. But what's the actual answer? It's about 4.5 times 10 to the negative 3. So we're very close. And let's just finish off strong with C here. So 10 MeV, go to 10 MeV, cap over rho, bring it over, get about 4 times 10 to the negative 4. And we can set up our Z dependence ratio. We get a value of 13.7. We can multiply them together. We get approximately 5.5 times 10 to the negative 3. What is it actually? 4 times 10 to the negative 3. So these values, I got them from the same plot, but just for lead. So, I mean, obviously there's some error in these. Okay, so problem 5. Also, yeah, so I'm going to go through a couple questions. They're just sort of general refresher questions, just to give you a nice review. Okay, so what is photoelectric effect? It's the interaction between a photon and atomic electron, in which the photon's energy is completely absorbed and the electron is ejected. Can photoelectric effect occur with the free electron? The answer is no. How much energy goes to the photoelectron and photoelectric effect? All of it minus the binding energy of the electron. So therefore, what's the formula to calculate the photoelectron's kinetic energy? It's this is the kinetic energy is equal to HV minus binding energy. So simple enough. For E, what do you call an atomic electron ejected from an electron-electron collision? It's a delta ray. For F, what can happen when an M shell electron is released or ejected? And just to be clear, the M shell is not the outermost shell, so there's further electron shells past M. Just to be clear for our answer. So essentially, the filling of the M shell electron by an outer shell electron will create characteristic radiation, and there also might possibly be the creation of an Auger electron. For G, what's an Auger electron? So the filling of an inner shell vacancy is accompanied by the emission of an electron. Okay, problem 6. So what is Compton scattering? So when an initial photon collides with an electron, the result is a photon scattered with less energy and an electron scattered with kinetic energy. What does a labeled Compton interaction look like? So this is it. You have initial photon coming in, interacting with an electron. The electron scatters off with a kinetic energy, and a new scattered photon has a new energy, HV prime. Notice the angles of each of the electron and the scattered photon. The electron is denoted by theta. Scatter photon is denoted by phi. So be very careful here with these two designations, because when you're actually performing calculations, it's going to show us, for example, a theta. You have to know if that's the angle from the electron or from the photon. So it's very important to memorize this diagram. Okay, so let's go through the Compton formulas. Part C, what is the Compton formula for calculating the energy of the scatter photon, HV prime? So this is the formula. This should be, you should have this memorized. HV, initial photon, HV prime, scatter photon. MOC squared is the rest mass of the electron, which is 0.511 MeV. We will go through example calculations in the next problem for Compton. 1 minus cos, this is phi. This is right here where the scatter photon is. And be careful with your brackets. Notice that these two terms are going to be multiplied by the result of these terms. And then you add 1, noticing the brackets. So this addition operation isn't done first in this. So you got to be careful. So for part D, what are the Compton formulas for calculating the electron's kinetic energy? Focus in on this formula. This isn't really necessary. If you do need this formula, you could simply sub in the formula for HV prime and work it out. So this is the formula for calculating electrons' kinetic energy, initial photon energy, and this is the scatter photon energy. Subtract them. E, what is the formula for calculating the angle of the electron? So this is a rather tricky formula to memorize, in my opinion. This is cotangent. Here's theta. So that's the angle for the electron. Phi. Remember, it was tricky too to memorize is tan phi over 2. So these three formulas should be memorized. 1, 2, 3. And the diagram should be memorized. You don't need to memorize that. Okay, so let's actually go through some practice problems with these formulas. So problem 7. Initial photon with an energy of 20 MeV interacts with an electron by Compton effect or Compton scatter. What's the energy of the scattered photon after it scatters with an angle 90 degrees? So we have that formula again for the energy of the scattered photon. 7 are values. Initial photon 20 MeV, rest mass of electron 0.511 MeV, scattered at an angle, scattered photon at an angle 90 degrees. We can go ahead and solve. Part B, calculate the kinetic energy of the electron. So it's just your initial photon energy minus your scattered photon energy. In part C, calculate the scattering angle of the electron. So we have that formula. We can sub in our values. So we're calculating theta in this case. 90 over 2, that's tricky to memorize. Obviously watch the brackets. So we work it out and we get 40.139. Cotangent theta is equal to 40.139. But notice here that you can't calculate this on your calculator, right? There is no cotangent button on your calculator. So this is a sneaky, So how do you solve this? So as a refresher, I shall show you. So remember that cotangent theta is equal to 1 over tan theta. Cotangent theta is equal to 1 over tan theta. So we can rearrange for tan theta. We'll move tan over, so that'll be the inverse of tan. So theta is equal to this. And now we can solve. There is a inverse tan on your calculator. Be careful and make sure that your calculator is in degree mode. And we get our answer, 1.43 degrees. So that's 7 problems. That's the first 7 problems of photon interactions in this video, the first video, and I'll be following through with problems 8 through 14 in the second video. So thank you very much for watching, and I'll catch you on the second video. Bye.